Hello and welcome back. I'm going to say something that's going to sound really clickbaity, but it's 100% true, which is that bacteria are winning the war against antibiotics. And it is an inevitable future based on very, very logical steps that are taken along the way that's going to lead to the inevitability of bacteria and multibacterial resistant organisms running today. It sounds like science fiction, but I promise you it is something that could be part of our future if things aren't done now, where a routine surgery or like a scraped knee could stop being something that we can treat really easily. If you cast our mind back to, let's say, 100 years ago, where things like dental abscesses were things that could kill people, and it's not even a thing that we think about today. And it won't be because bacteria has somehow gained the superpower to evade all antibiotics. It'll be because we've built a system that disenfranchises companies that invent those drugs, and those companies go broke. And I'm not fear-mongering, this has already happened, and it'll probably something that will continue to happen down the road if things aren't done now. My name is Vicky, I'm a pharmacist, and I'm also a medical science liaison. And if stories like this interest you, well, please click the subscribe button or comment and like. It'll tell me, what I'm doing well and what other topics I should explore in the future. So there are three things that are happening at once. First is that antibiotic-resistant bacteria are climbing. Second is that the supply of new antibiotics has almost run out. And third is that there are almost no companies that are willing to make new antibiotics or to invest in the research for new antibiotics because the economics just doesn't make sense. And I'll go through each point one by one. And I do want to emphasize that along the way, everyone is making logical choices. There's no supervillain out to destroy the world. It's just every regulatory company, every healthcare professional is doing exactly what they think is the right thing to do. And this is a trap that economists call the tragedy of the commons. By the way, I apologize for any construction noises. There's a lot of construction going on outside my home right now. So if you can hear extra noises, I'm sorry. It's not me, it's them. So first, let's put some numbers on it. In 2019, drug-resistant infections directly killed 1.27 million people. It also was a part of close to 5 million deaths. So that number is more than HIV and AIDS. It's more than malaria. In 2024, a research group called the GRAM Project put out the first look at how resistance has moved over time from the 1990s to 2021, with projections running to 2050. Their central estimate is that more than 39 million people will die directly from a resistant infection between 2025 and 2050, which means approximately 3 deaths per minute over the next 25 years. Let's put some names to these abstract resistant bugs. So for example, MRSA, methicillin-resistant Staph aureus, is one of the most common drug-resistant bacteria in the world. And it has doubled its death toll from around 57,000 in 1990s to 130,000 in 2021. But generally with methicillin-resistant Staph aureus, we have drugs such as vancomycin to treat it. The drugs that really make pharmacists and infectious disease doctors cringe are the multi-drug-resistant gram-negative bacteria. Those bacteria are much harder to treat because they have an extra membrane around them, and that makes them tougher to kill. So about 10 years ago, we would have used something called carbapenems to treat those multi-drug-resistant gram-negative bacteria. They're what we consider the heavy guns, the artilleries. And now carbapenem-resistant Staph gram-negatives are climbing, and that sends a chill through every infectious disease doctor and pharmacist's spine. Now, how do drugs become resistant? Well, through overexposure of antimicrobials. Because bacteria is really good at dividing. It's really good at replicating. And a single colony can churn out more bacteria in a day than humans can in the entire recorded history. And as they divide and replicate, their DNA or RNA has a chance to mutate. They could pick up a mutation along the way or just by simply through random chance. And so this is what happens when you flood a colony with antibiotic, is that it will kill off all of the ones that are not resistant to it yet. But there may be one or two that remains that is partially resistant or completely resistant. And then those bacteria will continue to divide and proliferate. Now, these resistant genomes aren't just passed down from parent to child, they're also passed down, well, by picking things up along the way, because bacteria have what's called horizontal gene transfer. So they don't even have to divide and mutate to gain a new mutation. They could just pick it up along the way, like a text from a stranger. And this is how, one resistant gene can go from one particular bacteria to another type. So like Staph aureus to Staph epididymis. Staph epididymis. And that means every time we're using an antibiotic, we're applying that selective pressure to selectively select for the bacteria that have that resistance to that particular antibiotic. In infectious diseases, it's often said antibiotics is kind of like a melting ice cube, because the moment you start using it, it starts to be used up. The moment you start to use a novel antibiotic, you're expecting that somewhere along the line there will be a resistance to this antibiotic. It's just a matter of time. While we can, blame the overprescription of antibiotics to anything and everything, like, for example, using antibiotics to treat flu, which won't work, the biggest culprit isn't us, it's agriculture. By sheer weight, the majority of antibiotics used all over the world goes to livestock and not human, and it's estimated that about 2/3 of the antibiotics used goes towards things that we eat. And a lot of those antibiotics are used for preventative measures, not to treat sick animals, but to prevent diseases from popping up. And that is a logical choice if you think about it from the farmer's end. You would rather stop a disease before it even has a chance to spread. But by using so much of those antibiotics, you are selecting for resistant bacteria. And those resistant bacteria don't just stay in the farms. They go everywhere, into the soil, into the water, and then some other bacteria along the way just picks it up through that horizontal gene transfer, and there you go. Given that we know that mutations and resistance is just on par for the course and inevitable, then, the only way to stay in this fight is to invent new antibiotics, right? And I'm going to illustrate this with the use of penicillin and methicillin-resistant Staph aureus. Penicillin showed up in 1940s, and it was a miracle against staph. It was highly effective, and it killed bacteria by inhibiting the synthesis of cell walls. And gram-positive bacteria need to have a cell wall that is structurally sound. Without a structurally sound cell wall, they kind of burst open and die. And so it was a really great way to kill gram-positive bacteria. And what did Staph aureus do? It picked up a gene or mutated a gene that encodes for an enzyme called penicillinase, and that penicillinase, as its name implies, breaks down penicillin. It finds the exact part of the penicillin molecule that acts against Staph aureus, which has a beta-lactam ring, and it snips that open, and penicillin no longer works. And because of that, in about 10 years, almost all of the Staph aureus became resistant to penicillin. And so scientists set off to find a better alternative, and they invented something called methicillin. And methicillin is basically like an engineered better version of penicillin, and it is designed so that penicillinase wouldn't be able to grip onto it. They essentially took the beta-lactam ring out of reach of penicillinase, and it was a beautiful design. But then, about a year afterwards, methicillin was introduced in 1959, and then in 1960, the first methicillin-resistant Staph aureus came onto the world. And how it did that was through a gene called MEK-A. And MEC8 encodes for a protein that's kind of like a backup penicillin binding protein, therefore called PBP2. Now, PBP2 can also build cell walls, but it is built in a way that penicillin and methicillin can't grab onto it and make it ineffective. And so that's how it managed to become resistant to both penicillin and methicillin. So think of it kind of like the bacteria, instead of trying to destroy the enemy's weapon, it just built new machinery that the enemy's weapon can't destroy. And I hope this illustrates how well bacteria can adapt and shift against, us. And this, essentially an arms race to see who can, have better defenses, who can have better weapons. Except for us, our incentive of building more weapons against the bacteria is kind of waning. Because the truth is that almost every antibiotic they've ever taken came from a class in the 1940s and in the 1950s. There are incredibly few novel antibiotics with new mechanisms of action that are being discovered or even marketed today. And most of the new antibiotics that are, on the market aren't really new in that they have a different way of acting on the bacteria. They're really just tweaks of the old ones, like how methicillin was for penicillin, to overcome the defenses of the bacteria. And WHO's report in 2025 said exactly that. Of the 90 antibacterial candidates that are being investigated, only 15 are truly novel in the way they act, and the rest are just like tweaks of old drugs. In a previous video, I said that most of the drug developments never make it to marketing. It's only like 1 in 20. So even though I say there are 90 candidates in the pipeline, chances are it's only going to be like a fraction, teeny tiny fraction, that will actually make it to hospitals. And compare this to something that's like oncology, which would have thousands of candidates that are being worked on right now. So given that there seems to be this big market for new antibiotics, why isn't there a drive, a push to get new antibiotics out into the market? Well, you have to dive down into the economics of making a drug and getting it to market. Antibiotics are some of the most needed drugs, and yet they're the least profitable to sell, because usually it is one time and done, as opposed to, let's say, blood pressure medication or the cholesterol medication, the GLP-1s. Those people have to take consistently on a daily basis, but you don't have that for antibiotics. Usually the course treatment is a week, maybe 2 weeks at most, and then that's it. You'll likely never see this patient ever again. So it is usually a one-time thing. Now, if you're thinking as a drug company would, that first it's going to take millions just to develop this antibiotic, then to take it through phase 1, phase 2, phase 3, which again takes millions. Like a conservative estimate would be somewhere around 60 million, maybe to $1 billion, just to take it through that, and then go through all the various regulatory affairs in each country. Like in Canada alone, it's $500,000 minimum to just go through our health agencies. And then, you think about all those other countries, the US, and the cost rapidly goes up, right? And the patent doesn't last forever. So patents usually start at the time of when you submit to a regulatory agency that there is this new proprietary molecule, to when it's off patent is about 10 to 20 years, which sounds like a long time, but you have to remember that majority of that time, 10 to 15 years, are going to be stuck in trials and then regulations, so that by the time the drug is out on the market, you have about maybe 5 to 8 years to get all the costs that you have put into this medication back. And that's one of the reasons why new antibiotics are really, really expensive. they kind of have to be. But that cost is also, one of the reasons why like health agencies kind of hesitate to approve because they're so expensive, and hospitals don't want to use them because they're so expensive. And then, and in addition, infectious disease pharmacists and doctors don't want to use shiny, bright, new antimicrobials because they know that once they start using it, then it's just a matter of time before resistance comes in. So they want to save it for as long as possible. And all of these are really, really logical choices, right? But you can see how then the drug companies don't have the incentive to develop antibiotics because there's no money to be made. And this isn't just like a thought experiment because it has already happened to 2 drug companies. First is Achaogen. I'm probably pronouncing that wrong. It's Achaogen. Someone please correct me on the pronunciation if I'm pronouncing it wrong. They made a drug called plasmomycin, and it does target carbapenem-resistant gram-negative bacteria. And the FDA approved it in 2018. And the quarter prior to FDA approving it, the company was already going bankrupt. Achaogen filed for bankruptcy in 2019 and had to lay off all of its scientists and staff and personnel, and the patents overall were sold for $16 million, which is much, much, much less than what they had put in. And in the same year, Melinta Therapeutics also went under, and they had 4 antibiotics. And none of their antibiotics, failed the trials. They all worked. It was just that there weren't enough profit to be made to keep the companies afloat. So if you think about that, like both companies made drugs that the world needed, and yet they went bankrupt. And the other companies read the room and made appropriate business decisions. There was many big companies that saw what happened to Melinta Therapeutics and Achaogen and decided to fold the antimicrobial division. Novartis, Sanofi, Allergan, they all decided to shut down their antimicrobial pipeline. And when I was a medical science liaison, one of the products that I had under my portfolio was an antibiotic called CIDRAP or dalbavancin. And it was an antibiotic that worked against gram-positive bacteria that a lot of clinicians were like, wow, this is really good, especially for certain surgical infections. But did they use it? No. Because it made sense for them to try to, treat the infection with first cheaper alternatives that they think would, be able to be used. And secondly, the hospital formularies was hesitant approving it unless there was, like vancomycin-resistant bacteria or something like that, because they were like, it's so expensive, and yeah, there was a whole slew of reasons. And here's the thing, right, is that, every step along the way, people are behaving rationally. They're behaving logically. They're behaving according to the market demands and needs. The doctors that aren't prescribing it aren't being careless. They're doing what good stewardship would do. And those stewardship programs try to promote like responsible prescribing. So, don't use antimicrobials when you shouldn't be using them. Minimize the duration, things like that. Use oral instead of IV if you could. Like, those are good decisions to make, and they're good for patients. And the companies that want to prescribe generics first instead of like the brand new shiny antimicrobial is being very, very fiscally responsible, even though it would bankrupt the company that makes the medication. And then the companies that are making this medication takes a look at the market and goes, well, I can't afford to be here. If I really want to do this, I won't be able to make any money. And even investors will look at this and say, well, there is no money to be made in antimicrobials. Why would I try to invest in that space? So is it too late? Are we marching towards a hopeless future where bacteria will win against all of us in spite of our best efforts? Is that going to be the future? Well, In order to avoid that future, we have to change the incentive. We have to change what's called a pull incentive. The idea is to change what the companies are getting paid for. Right now, companies are paid per prescription or per pill, which puts them at head-and-head odds with antimicrobial stewardship clinicians. A better way to change the pull incentive would be to reimburse the company for there simply being this antibiotic option out there, no matter how little or how much of it is used. And UK is already doing this, where the NHS pays the companies in matters of like millions each year to have access to these medications, regardless of how much they use. In the US, there is a proposed law called the PASTEUR Act that would do something similar, which would give developers of critically needed antibiotics big contracts that aren't tied to sales. But it hasn't been approved yet. Like, it keeps on getting introduced and it keeps on not passing. Meanwhile, there is an AMR, so Antimicrobial Resistant Action Fund, which is about $1 billion effort backed by industry that would help and keep small players that are developing new antibiotics alive, and enough for the policy to catch up. So what does that really mean? Well, we are staring at a future that is increasingly getting scary unless the policy changes. And WHO has recommended for each health agencies to consider backing those little companies because of this sort of inevitability. I think the core story in all of this is that everyone is acting according to logic. But we can also change that logic by changing the policy. If the policy now incentivizes companies to keep on developing these critically needed medications, even though there may be no, obvious financial backing and things like that, then it would keep that pipeline alive and keep us in this arms race for longer. Now, if you enjoy this content, please subscribe, like, comment. This will really, really help me. And let me know what you think I should talk about next. I'm thinking about more peptides, but maybe I should also talk about policies. Like, for example, drug price negotiations. Having been on both sides of the table, it'll be interesting. It'll be an interesting discussion.